Hey all you cool cats and kittens, it's Miss McKinney again. How's it going? It's day something or other of distance learning. I've lost count. Um, but today I wanted to talk to you guys and remind you about balanced and unbalanced forces and Newton's laws. First up, balanced and unbalanced forces. If something is either not moving at all or moving at a constant rate, it is going to be balanced. For example, all of these books behind me, they are balanced forces. Their net force is 0. If we added and subtracted all the forces acting on the objects, it would be 0. For example, this book behind me, right here, it is exerting a force downward due to its mass and gravity. And the bookshelf is exerting a force upwards that is equal to it, so the net force is going to be 0. If it was not 0, the book would either be going up or going down. All right? So to find the net forces, you look at the direction that the forces are going and the numbers. If they are going to separate directions, we're going to subtract. You're not going to get a negative number, just subtract the smallest from the biggest. If they're going the same direction, you're going to add them together. If they're going like this, guys, that's still opposite directions, because if you just keep going, one's going to the right, one's going to the left, even if they're pointing at each other. All right? The numbers do not equal 0. It is unbalanced, which means there is going to be a change in motion. If it's stopped and it starts moving, that's due to unbalanced forces. If it's moving and it either speeds up or slows down, that is due to unbalanced forces. Or if there are arrows, the object is going to move the direction of where the larger force is taking it. If the larger force is pushing, then it's going to go in the direction that it's being pushed. If the larger force is pulling, it's going to go in the direction that it's being pulled, right? So, to sum up balanced and unbalanced forces, if the net force is 0, if you subtract all of the different forces acting on an object and it's 0, then it is balanced. There will be no change in motion. If it's going at a steady speed in a steady direction, it will continue going like that. If you threw a baseball from your spaceship window and it did not get caught by anybody's gravity and did not bounce off of any other space objects, it's just going to go the same speed and direction that you threw it forever. Balanced. You sitting in your chair, not moving, balanced. And now that we have the basics of balanced and unbalanced forces down, we can talk about Newton's laws. Remember, there's 3 of them. The first one is the law of inertia. That one states that an object at rest will stay at rest, an object in motion will stay in motion unless acted upon by an unbalanced force. Oh, an addendum to that. An object in motion will stay in motion, constant speed, constant direction, unless acted upon by an unbalanced force. First part of that is pretty simple. If you have a soccer ball laying on the ground, that soccer ball will continue to stay on the ground unmoving unless a greater force comes by and changes it. Somebody kicking the soccer ball will obviously move it. If it's balanced on a hill and gravity starts pulling, well, gravity always pulls downward, but gravity affects it by pulling downward and causes it to roll down the hill, that is an unbalanced force. Wind, if it's still and then a big gust of wind comes by, that's an unbalanced force, and it will cause it to change its speed and or direction. So an object at rest is going to stay at rest. The other side of that, an object in motion stays in motion, same speed, same direction, unless acted upon by an unbalanced force. This, guys, is why we wear seatbelts. If you are driving along in your car at 75 miles an hour and your car suddenly stops because you hit a wall or something, your body is going to continue to go same speed, same direction until an unbalanced force stops it. And normally that unbalanced force that stops it, if y'all are smart, will be your seatbelt. That's why we wear them. Otherwise, it could be the windshield, the tree, the wall, etc. If you have ever tried to stop running really, really fast, you know what I'm talking about. You run, you see something, you try to stop, your feet stop, your body just goes and crashes down. Or you'll slide and then fall. No matter what way you do it, it's never fun. So there are different forces that will stop you. The main one, the force that always works against movement in every situation, I know y'all have heard this like a million times, is friction. That's why we get the rug burns or the grass burns if you fall and you're wearing shorts. Friction slows things down always. When that soccer ball starts to roll down the hill because of gravity, it just doesn't keep rolling forever, is because eventually the friction of the grass or the ground will cause it to stop. There are some things that have more friction than others. Grass obviously has more friction than an ice skating rink, right? It's the tendency of an object to resist changes in its motion. The bigger something is, the more inertia it has. Well, the more mass something has, the more inertia it has. It would take a whole lot of force for me to try to move these bookshelves behind me, because they have a bunch of books on them, so they're really heavy. Plus, they're bolted into the wall so they don't fall over on top of me. So they have a lot of inertia. It would take a lot of force to get them moving. They're going to stay right where they are, hopefully. The second law, force equals mass times acceleration. Y'all covered this earlier when we did the triangles. That's just basically it with the formula. But what it means in scenarios is that the more mass something has, the more force it is going to take to speed it up. Think of grocery carts. Which is easier to push? Which can you push faster with less effort? An empty grocery cart or one filled with bags of cement? Obviously, the cement is going to be harder to push because it has more mass. More mass means it takes more force, and it is going to go slower. So mass and acceleration are inversely proportional. If force stays the same, your mass goes up, your acceleration is going to slow down. If your mass goes down, we start taking those bags of cement out of your shopping cart, the acceleration is going to go up. You're going to be able to push it faster. If force stays the same and you increase the mass by 2 times, acceleration decreases by 2 times, right? So while mass and acceleration are inversely related, that means that force and acceleration, or force and mass, are directly proportional as long as the remaining variable stays the same. If we have something accelerating at 5 meters per second and I increase the mass that I put in there, the force is going to increase by that much as well. If the mass triples, the force triples. Same way with acceleration. If mass stays the same, but I push something 5 times faster, it's going to take 5 times more force for it to go. So, force and acceleration and force and mass directly related. One goes up by 2, the other goes up by 2. Okay? But acceleration and mass are inversely related. And that, my wonderful students, brings us to the third and final of Newton's laws. For every action, there is an equal and opposite reaction. Okay, remember, opposite and equal are the key terms there. If I throw a bouncy ball on the floor, which I'm not going to do because it's in my house and I'll probably break something, the force that it hits with is rebounded and it goes up using the same amount of force. This goes for everything. If you take your hand and you slap the table lightly, or I'm going to use my other hand so y'all can see it. I didn't hit with much force, so not much force was rebounded in my hand. But if I take it and I slap the table or the bookshelf really, really hard, it's going to make my hand hurt because the force I hit with, there is an equal and opposite force that goes back into my hand because of it. The thing called action-reaction pairs or force pairs. Pair means two, not the fruit, like a pair of shoes. And the important thing about force pairs is they have to be touching. Right now, my Dare to Cook sign, it is sitting on the bookshelf. So half of the force pair is the sign, the other half is the shelf it's sitting on. If my car is on the road, my car is part of the force pair or the action-reaction pair, the road is the other. Now, back to action, opposite reaction, speaking of cars. So we already talked about having the seatbelt is important because that stops your body from crashing through the windshield if you get in an accident because of inertia. Now, when you're wearing that seatbelt, you may notice that when you slam on the brakes, your body goes forward, but then when the seatbelt catches you, you go backwards as well. The harder you go forward, the harder you go backwards. That's why a lot of times when people get rear-ended, they get whiplash because they go forward, the seatbelt catches them and swings them backwards like that, which upsets your neck. But that's a lot better than going through the windshield, right? The more force you are going forward, the more force you're going backwards. Think about when you're walking. You're pushing your foot backwards to send you forwards. The more force you use to go backwards, the faster you go forwards. That's why when you're watching races, people will kind of crouch, kneel down, and then push off with their back foot because that gives them more force to go forward with their start. If you ever go swimming and you wanted to get across the pool fast, you crouch up as close as you can with your feet on the sides of the pool and then push off. You're pushing backwards with your feet, which sends you forwards. This third law of action-reaction, remember there has to be some kind of opposite reaction there as well. Some you can physically see, like if you bounce a ball, again, the harder you bounce it down, the higher up it's going to go and the faster it's going to go. That's easy to see. Some are more difficult to see. Like, I know we mentioned this in class when some of y'all told me that you've punched a wall before. The harder you punch the wall, the more force that's rebounded back in your hand, which is why you could break fingers. You don't see the wall hitting you back, but that's basically what is happening. If it doesn't at least imply that there's an opposite or an equal and opposite reaction, it is not going to be Newton's third law if it's asking you scenario questions. All right, again, you wearing your seatbelt and your seatbelt stops you from going through your windshield, that is Newton's first law because that has to deal with inertia. The seatbelt catching you and then you going backwards and getting whiplash would be Newton's third law. So a quick recap, Newton's first law, inertia. Objects in motion stay in motion, same speed, same direction. Objects at rest stay at rest unless something makes it move. That something being an unbalanced force. That again is why when you make a left turn in your car, it feels like you're going to the right because your body is wanting to keep going straight. So when your car goes left, your body's still going straight, except that turns you to the right in your car. Newton's second law, force equals mass times acceleration. The heavier something is, the more force it's going to take to push it. The heavier something is, the slower it's going to go. And Newton's third law, for every action there is an equal and opposite reaction. Equal and opposite, not just reaction. Also, force pairs, there are two of them, and they have to be touching. One is exerting the force, say, downwards. The other would be exerting the force upwards. So that is all I have on Newton's laws and balanced and unbalanced forces for this week. I hope that helps you out with your packet if you need it. Since I'm here, might as well ask, how are y'all doing? Everybody staying sane? I'm trying to. I've discovered that I really like growing succulents, and I now have about 20 of them in various teapots that I found around the house, or teacups, and I even bought some beakers off from walmart.com to be delivered, so I'm making super cute science-y ones. We'll see if they live. I hope so. This one is already kind of... the cat was trying to eat it, so it has holes in it. Yeah, the cat that you saw in the first frame. She really likes being on me when I'm trying to work on the computer and doing grades. Lots of fun. So I hope everyone's doing good, and if you need any more clarification on this, you know how to get a hold of me. I miss you guys, and I hope to see you before the end of the year.